Hi, welcome to my talk about RISE, a functional pattern-based language in MLIR. I'm Martin Lücke, a first-year PhD student at the University of Edinburgh, and my two supervisors are Michael Stoiber and Aaron Smith, and this is work supported by a Google Faculty Award. And first, let's talk about our motivation here. So this is a recent Hot OS paper by two of the original TensorFlow authors, Paul Barham and Michael Isard. And they argue that machine learning systems are stuck in a rut due to a number of reasons. For example, the hyperoptimization of large monolithic inflexible kernels like matrix multiplication. And they think that the current programming abstractions we have lack expressiveness and modularity, and that all of this hinders research progress. So they argue that we should aim for more principled, higher-level intermediate representations. And we want to tackle this and achieve more flexibility and modularity and so on by breaking up these large monolithic kernels into compositions of smaller building blocks. Which brings us to RISE. So let me give you an introduction to our functional pattern-based representation. Here we look at the example of a matrix multiplication. So to compute the yellow output element of matrix C, we perform the dot product of all the green values in the row of A with all the red values in the column of B. And this means to compute the full matrix multiplication, we have to compute the dot product for all rows in A with all the corresponding columns in B. And when we look at the RISE program above, we see that this is exactly how this program is written. The map pattern, which is highlighted in green, applies a function to all elements of an array. And as a matrix is just an array of rows, this applies a function to all rows of A. So for all rows of A, we do the following. And next, again highlighted in red, we have a map pattern which is applied to B transposed. So we do the following for all columns of B. So in an imperative sense, this means for all rows in A, for all columns in B, we do the following, what's in this blue box. And let's pick apart what's in this blue box. We zip the row of A with a column of B, such that we have an array of tuples of the corresponding elements. And for the dot product, we have to multiply these corresponding elements. So we map multiplication on this array, which means we apply it to all of these tuples individually in the array. So now we have a flat array of these multiplied values, and we sum it up to a single element using the reduce pattern. So we perform a reduction with the function addition and initialization value 0. And this concludes our matrix multiplication. And one of the main things you should note here is that the matrix multiplication is actually built out of the dot product by composition. And this means when we have an optimization for the dot product, it automatically applies to the matrix multiplication as well. And this representation is actually heavily inspired by Lift, and RISE is a spiritual successor to the Lift project. And Lift has demonstrated optimizing programs by rewriting them, achieving high performance with this approach, and performance portability. So let's look at these bits really quick. So we start with a high-level program, which is a composition of simple and generic patterns, as we've just seen. And this one is optimized using a rewriting system. And the rewriting system consists of many rewrite rules, which we know are semantics preserving. And this means we don't change what is computed, but we only specify how it is computed. So by applying different rewrite rules, we generate many different low-level programs out of this one high-level program. And these different low-level programs are differently optimized because different rewrites have been chosen. And this means we can generate programs optimized for different hardware architectures from the single program on top. Next, let's look at an example of a rewrite rule. For instance, here we apply a function f to all elements of an array A. And in the rewritten version, we partition the array into smaller arrays using split and apply the function to the individual elements of these partition arrays with map. And you can think about this now, that the rewriting system performs another rewrite later, such that the outer map is performed in parallel and the inner one sequential. And this might help exploiting locality. And you see the parameter n in the split, there becomes the parallelism granularity factor. And here we have some performance numbers for matrix multiplication, which were published at GPU 16. And in the top left figure, we see performance on the y-axis and the number of kernels that achieved this performance on the x-axis. And we see the graph is very thin on top, so this means only very few kernels reach very good performance. But in the right-hand figure, we see that we can still expect to find a good performing kernel quite quickly. And in the bottom figure, we see that the performance of the best performing kernel is close or even better to hand-tuned library code. So I know the only question you're asking yourself right now is, why are people still handwriting and optimizing, for example, CUDA programs, and why is not everyone using this system right now? And the main problem is the majority of people are used to writing imperative code. And it's hard to convince performance engineers who are used to writing low-level code to program in the zipmap reduce style and leave the majority of the optimization to the compiler. And furthermore, Lift is an academic work written in Scala, which means it does not integrate well with other existing compiler infrastructures and toolchains. So the question is, how can we integrate with existing solutions to achieve an end-to-end integration? And let's say we want to start with a machine learning model such as MNIST for handwritten number classification in TensorFlow, and we want to compile and execute it on some given hardware. And while doing this, we want to leverage all the advantages of the functional pattern-based representation we have just seen. Okay, so the last part of the title is in MLIR, so let's talk about MLIR. MLIR is an overloaded acronym with different possible meanings, but my favorite one, of course, is Martin Lücke intermediate representation. But for the purpose of this talk, let's stick with multi-level intermediate representation. So MLIR is an infrastructure to define compiler intermediate representations, which are called dialects. And multi-level here represents that different dialects can capture different levels of abstraction. So we could either have a very high-level domain-specific dialect, for example, for stencils, but we can also have a dialect which is a very hardware-specific backend. And the dialect we are presenting here today is leaning towards the left side of this range, but it's still not really domain-specific, as Lift has shown to generate good code for various domains. But it is still a high-level abstraction. And the MLIR infrastructure already contains existing dialects, for example, for TensorFlow, for targeting GPUs, or to perform polyhedral optimizations. And this MLIR infrastructure opens up many opportunities. As it is written in C++, integration into other toolchains is far easier. And having RISE as a dialect inside that infrastructure means that we can integrate and interact with other dialects as well. So this means, for example, we don't have to write functional programs ourselves, but we can lower from other domain-specific representations to it. Here, for example, we can utilize that an XLA HLO dialect already exists. This means we can use the existing infrastructure to lower the TensorFlow model to this dialect, and we are already in the MLIR world. So now we only have to figure out how we lower from this dialect to the RISE dialect. So the first step in lowering a TensorFlow model to RISE is lowering it to the XLA HLO dialect. And we see a shortened version of the MNIST model in the XLA HLO dialect on the left-hand side. And there we match for supported operations, for example, matrix multiplications or convolutions. And in this particular example, we find two dots, so matrix multiplications in this case. And we replace them with the corresponding RISE operations on the right-hand side. So these are exactly the matrix multiplication expressions we've seen at the beginning. And in consequence, after these steps, all the operations we are interested in are represented in the RISE dialect. So in our end-to-end story, we now have a way to lower machine learning models to RISE. So next, let's look at how this RISE MLIR dialect actually looks like. Here on the left-hand side, we see the same example for the matrix multiplication we have seen in the beginning, and on the right-hand side, we see its representation in the MLIR RISE dialect. And I don't expect you to read all of that, but the thing to note here is that all the patterns we see on the left-hand side are also on the right-hand side, highlighted in red. And the structure is exactly the same. So we still have the map, zip map, reduce structure to model the matrix multiplication. So there's a clear correspondence. So let's take a deeper dive how we model this in MLIR. So we introduce some custom types. We introduce data types and function types. And the three data types we introduce are for arrays, tuples, and scalars. Here, for example, is the type of matrix A, which is an array of size 1024 of arrays of size 1024 of scalar F32s. And what you can note here is that multidimensional data is represented via nesting of arrays, which is very natural in this functional representation. And that our scalar type represents an arbitrary scalar type Here, for example, it wraps an F32 from the standard dialect. And function types are the types of our lambdas and our patterns. So here, for example, the type of the lambda is a function type from tuple of two scalar F32s to a single scalar F32. And our type system prevents mixing of function and data types, so you can never have a tuple of functions or an array of functions. Next, we look at patterns. So let's, for example, look at the example of zipping the row of A to the column of B. So we look at this zip pattern. And the zip pattern is implemented as an operation. And this operation is customized with the additional information we need for its type, such that this zip operates on arrays of size 1024, which both contain elements of type scalar F32, which are basically floats. So in consequence, the type of percentage zip is a function type with exactly these two array types as input and an array of 1024 of these tuples as output. So for each of our patterns, we introduce an operation. And next, we look at function application. So again, we look at the same zip example, and we model the application of these patterns explicitly. And we do it by using the rise.apply operation. And rise.apply takes a value with a function type, which is the applied function, as input. Here, for example, the percentage zip is the function to be applied. And one or more values, which are the arguments to this function, and have to fit its type. These are percentage A row and percentage B call. So these are the input to the function zip. And in consequence, the type of the result is the output of the function type of the applied function. So here it's, for example, an array of size 1024 with tuples of two scalar F32s as elements. And next, we look at how we lower such a rise program. So let's first look at the high-level overview again, because again, there exists a substantial amount of infrastructure already. So let's first talk about the affine and the standard dialects. The standard dialect contains a collection of often used operations, such as computations like addition or subtraction, and operations for loading and storing data. And the affine dialect captures polyhedral compilation concepts, so we can also leverage them, and it has a notion of loops. So for example, there's an affine.loop. And from these two dialects, there already exists the lowering to the LLVM MLIR dialect. And the LLVM MLIR dialect has a one-to-one mapping to LLVM-IR. So this means when we lower rise to a combination of affine and standard, we can transitively lower our representation to LLVM-IR for execution. So here on the left-hand side, we see the matrix-matrix multiplication represented in rise from before. And on the right-hand side, we see the same computation in the affine and standard dialects. So we see the three loops and the usual access and computation structures of a textbook matrix-matrix multiplication in the affine and standard dialects. And we want to lower the left functional pattern-based representation to this target representation. So for now, let's shift the target representation to the right for a second, because our approach is a two-step process. The first step is lowering the functional representation on the left to an imperative representation, which here is in the middle. And on the left-hand side, we have the patterns like zip, map, and reduce. And in the middle, they have been lowered to loops, indexing computations, and assignments. So here I colored a pattern, and the code it is lowered to in the same color. So for instance, the reduce pattern, which is highlighted in yellow, is lowered to the yellow code in the middle. So the reduce pattern is lowered to a loop and an indexing operation for the reduction, and the assignments to the accumulator. And the second part of this process is lowering the imperative representation in the middle to the target representation on the right-hand side, which here are the affine and standard dialects. So we start already in the imperative world, and we perform this lowering by resolving all indexings and finish up by generating all necessary load and store operations. For instance, the multiplication in line 10 depends on two values for matrix A and matrix B, which we have to load before the computation. And we also generate a store for the result of the reduction in line 12. So in conclusion, we now have an end-to-end system where the input is a model from TensorFlow, and we compile it progressively by lowering it using the MLIR infrastructure, including the rise dialect. and finally we emit LLVMIR for execution. But another thing is, there already exist a bunch of libraries which have highly tuned implementations of some operations, and we want to also be able to target them. So what we can do instead of generating code directly is we can match for a specific composition of patterns in RISE, for example the composition on the right hand side. And this is also exactly the matrix multiplication we've seen before. And when we see this composition, we can just replace it with a library call which we know has good performance. So we only have to look up all the info we need for the call in the RISE representation, for example the input size, and generate the call and the additional information for it. For example, here is a call to the MKL library by Intel. So finally, here we see our complete approach to an end-to-end integration. We progressively lower the TensorFlow machine learning model through the XLA dialect, can leverage the advantages of the functional representation in the RISE dialect, and we lower through the affine and standard dialect to the LLVM dialect to emit LLVMIR finally. And we can also target libraries. So let's look at a short demonstration of this. Here we have the file imnist.mlir, which already is the XLA HLO representation of imnist. So if, for example, you see we have a predict function and there's also a dot computation in there, and we start compilation with it. And we progressively lower through the dialects I've presented to you, and we finally execute. And we see that the input image has 90% probability of being a 2 and 10% probability of being a 7. All the work I've presented here to you today is open source, so you can find us on GitHub. We are very excited to hear about your comments and maybe ideas, and thank you very much for listening.